False. A translation is a linear transformation. False. That's why we have to use the homogeneous coordinates, yeah, because you can't create a translation by matrix multiplication, yeah, unless you expand the coordinates. Okay, so the point 2, 3 has homogeneous coordinates 2, 3, 1. True. So we're just saying, okay, so we're going to work, rather than in the XY plane, we're just going to work 1 unit above the XY plane. And true or false, PlayStation 2 has spectacular graphics?
No correct answer.
Yes, either I will accept either answer. True or false? Give yourself credit. Okay, so slight change to our schedule because I have to take the 24th off, so I won't be here on Friday the 24th. So you're going to use that as a catch-up day, and so you don't miss anything. Friday the 17th was supposed to be a quiz day where we spend the whole class doing like a group quiz and then an individual quiz. That's going to be just a take-home quiz. Okay, so we'll actually do material on Friday. The rules of the take-home quiz have not been established yet. I will let you know on Friday. So take-home quiz Friday, it'll be due Monday, and we're just going to cover material on Friday, Monday, and Wednesday so that Friday you could use as a catch-up day. And then we'll be right back where we're supposed to be. Yes. Because this textbook is designed to work for like 3 different kinds of courses. You know, a standard linear algebra course, or it can be used as a more advanced course. I can't remember but for the course that we're doing, like we're going to cover that material. It's just going to show up later in the book. So it kind of spirals around, and we don't have to go straight through. So yeah, small change. And then Friday the 24th, you guys can use as you see fit. Okay, so today we're going to see how matrix multiplication applies to creating computer graphics. So I'm going to take you through my notes on the reading, and then we'll use some of the things that I wrote up in the notes to solve some problems, and then you'll try some problems. Okay, so computer graphics are made up of pixels, right? A screen is just like a matrix of pixels. And the coordinates of which pixels to like show up are stored in a matrix, stored in matrices. So for whatever shape you want, you just have, it's just a bunch of coordinates, all the points of this shape, and you store all those coordinates in a matrix. And then you can manipulate the image, stretch it, shrink it, rotate it, reflect it. You can manipulate that image by just performing matrix transformations on the matrix of coordinates. So, but a translation we have problems with. We can't just use all the standard things we've learned so far if we want to do a translation, which is an important thing to be able to do in computer graphics, right? You need Zelda to be able to walk across the screen. So he can't just stay there getting bigger and smaller and rotating. He's got to be able to move. So we need to be able to perform translations, but translations are not linear transformations, which means they cannot be written as a 2x2 matrix transformation. So instead of using x comma y, we use homogeneous coordinates x, y, 1. Okay, so this keeps us working in a plane. It's just not the xy plane. It's 1 unit above the xy plane. And it allows us to be able to produce transformations via a 3x3 matrix multiplication. So if you want to send xy1 to x plus h, y plus k, 1, right? So we're shifting right h, up k. So if we want to be able to perform a translation, moving right and up or left and down, right? You take your xy1, that's your point that you want to translate, and you multiply by this matrix here, So it's hard to remember what all the different matrices are that you use to create the different transformations. This particular one, you've got the 2x2 identity here, and then you have HK1 in the right-hand column and fill in with zeros. So when you multiply that 3x3 matrix by XY1, 10H gets multiplied by your coordinate XY1, and you get X plus H. You get 1X plus 0Y plus 1H, X plus H. So you've shifted X to X plus H. Then we do the next row times XY1, you get 0X plus 1Y plus K, Y plus K. So we've shifted the Y coordinate by K units. And then the 0, 0, 1, the reason for that row is that when you multiply that by the vector xy1, you get 0x plus 0y plus 1, which is 1. So we're landing in the same plane we started in, z coordinate of 1. So xy1 gets moved to x plus h, y plus k, 1. So that's just the matrix that works. That's the matrix that we use to perform a translation. Any linear transformation, so anything other than a translation, if you want to stretch or rotate or shrink, anything in R2, any linear transformation in R2, and you want to use homogeneous coordinates because maybe you want to do both a linear transformation and a translation. So in general, we're always going to use the homogeneous coordinates because if you're working with computer graphics, you want to be able to do everything, translate, shift, rotate, stretch and shrink. So we're always going to use the homogeneous coordinates. So we already know how to make something in R2 perform a linear transformation. We know how to find the standard matrix that will make that happen. We've done it before. We'll review how to do it today. But so if you want to do it in a 3x3 matrix on homogeneous coordinates, you just find the standard matrix A that we have found before, and you sort of embed it in a 3x3 matrix in the upper left, and then surround it with a 1 in the corner and zeros everywhere else. So A is the standard matrix in the upper left. Then you put an L, zeros on the legs and 1 in the corner. So when you're doing 2D graphics, we're always going to use homogeneous coordinates and a 3x3 matrix multiplication to manipulate or move the image. And then an analogy to the 2D case, let's say we want to use XYZ1. If we wanted to do 3D coordinates, we would use XYZ1 to be the homogeneous coordinates for the point XYZ in R3. And when you're creating 3D graphics, you always use homogeneous coordinates and 4x4 matrix transformations to manipulate or move the image. And sort of the most important transformation that we can do for 3D coordinates is to project a 3D object into 2D, right? That's why we can visualize, that's why Wolfram Alpha can do all these amazing things, right? This is what it does. It takes a point in 3 space, X, Y, Z, 3 space, and it projects it into 2 space. And this is sort of like an artist technique. We just had to like really figure out exactly what the mathematics is that does that. So you've got a 2D computer screen. Let's use the wall. You got a 2D computer screen, right? And I have a model of a molecule sitting in front of me, and I want to create a 3D graphic that a scientist can manipulate and move around and look at, but it has to be 2D because it's on a computer screen. So the way you do it is you have this molecule. Every point on that molecule, you give a point in 3 space, X, Y, Z. It has coordinates. So we call this thing, the screen, the XY plane, and I'm sitting on the positive Z axis at 0, 0, some point D away from the screen. So I look at my molecule, pick one point on the molecule. It's got coordinates X, Y, Z. You follow the line of sight from me to the point to the XY plane. And where it hits the XY plane, that's the projection. We call that the projection of the 3D point into 2 space. So this is a little picture of it that I snagged from the book. So we've got the XY plane, that's the computer screen, right? And here's the viewer at 0, 0, D. And here's some point in 3 space XYZ. So the viewer looks at this point, and where that line of sight hits the XY plane, we call that point X star, Y star, 0, and it's called the projection of XYZ into 2 dimensions. So how to find the coordinates of X star, Y star, 0? It's basically, I mean, if you know how to deal with lines in 3D, you just find the equation of that line, figure out where it hits the XY plane. Those are the coordinates. But we have sort of a matrix shortcut to do it, right? The book used similar triangles to determine those coordinates. And then it derives from the similar triangles this matrix transformation. I'm not going to do the derivation for you. You can just use this. Why is there a row of zeros? In order to make the third entry of the result be 0, because we want to land in the XY plane. 0, 1, yep. So because we're dealing with 3 dimensions, a point XYZ in 3 dimensions, we're going to have to use the homogeneous coordinates in order to do matrix transformations on it. So we call it XYZ1. And we want to project that point into 2 space. I just want an X star and a Y star. So I can program where on the computer screen should I plot that point for the molecule. So this looks like a total mess, right? But this is the matrix multiplication you have to do. The projection of XYZ1, you do this matrix times the point XYZ1, and then you have to use this. I really shouldn't have drawn it like that scalar, because it's not really a scalar. Z is a variable. But so if you just do the first multiplication, the matrix times the vector, you land at x, y, 0, 1 minus z over d. And then just take this vector and scale it by 1 minus z over d, so that the last entry will be 1. So you divide everything by 1 minus z over d. So after you do this matrix multiplication, which is like, where the heck did that matrix come from, right? I'm not telling you, it's in the book. And like I said, it's just the line that connects the viewer to the point in 3 space to the XY plane. And this is just the matrix that represents that transformation. So after you do this multiplication, the matrix times the vector, you divide every entry in the resulting vector by 1 minus z over d, by the 4th entry, and you get x star, y star, 0, 1. We'll do an example, and it will be much clearer. Okay, so here we have a data matrix. So in computer graphics, the data matrices are huge, right? They have like gajillions of pixels, coordinates stored in them. We're going to do really teeny tiny examples just to get the idea of how it works. So here's my data matrix. Each column is a point. Okay, so I'm going to plot the point 0, 1, 0, 0, and 1, 0. So I've got a triangle. I've got this little triangle here. There's my data stored in my matrix. So on these axes, I want to sketch the image of this data under the transformation that scales the x-coordinate by 2, rotates 90 degrees about the origin, and then translates by 3, 1. No matrices yet. I'm just going to draw what it's explaining. Okay, so the first thing I do is I scale the x-coordinate by 2. So every x-coordinate has to get doubled, right? So these two stay the same because the x-coordinates were 0. Double 0 is just 0. And this guy becomes 2. Okay, so I scaled the x-coordinates by 2. All right, then rotate 90 degrees about the origin. So just take each of these key points, rotate 90 degrees about the origin. 0, 0 stays where it is. Where does 0, 1 land? Negative 1, 0. If you go 90 degrees about the origin, it lands at negative 1, 0. And Yeah, rotation is generally counterclockwise. And where does 2, 0 land? 0, 2. Okay. So there's my next version. So that's after 2 transformations, scaled x, rotated about the origin, then finally translate it by 3, 1. That means right 3, up 1. So we take each point and go right 3. Oops, I forgot to go up 1. Right 3 and up 1. So my triangle lands here. This is my final transformation. It's just 3 points. I was just doing a triangle to help me visualize it. It's really just 3 points. Yeah, your book goes into, there are more complicated computations that tell a computer how to connect the points, like which points need to be connected and whether they should be connected with lines or curves. So we're really boiling this down to like the bare minimum, just what happens to the points. Okay, so that's what we're trying to figure out, how to use linear algebra to do that, so that we could program a computer to do that, right? So we want to figure out what matrix multiplication will lead to those 3 transformations. Okay. So I have 3 points that I have to transform. So I'm going to put them in a matrix. My data matrix D was 0, 1, 0, 0, 1, 0. Okay, and I'm going to multiply it by a 3 by 3 matrix. Oh wait, I think I have to augment these, right? Yeah. I have to add 1s for the homogeneous coordinates. And then I'm going to multiply by a 3 by 3 matrix that will create my first transformation, which is to scale the x coordinates by 2. So I have to figure out what to put in this matrix to scale all the x coordinates by 2. This is the homogeneous coordinates of 0, 1, 0, 0, and 1, 0. Homogeneous coordinates just add a 1 on, right? So we're working not in the xy plane, but 1 unit above it. Okay, so this is my matrix that's going to scale x by 2. And I'm not going to fill it in yet. I just know there's some 3 by 3 matrix. We'll take every x coordinate in this matrix and scale it by 2. All right, and then I need some other 3 by 3 matrix that will do the rotation. Is it backwards? Yeah, why am I doing that? I'm asking you. So these are the points, right? So I have to, the first transformation is the scale x by 2. And the way you do a matrix transformation is you multiply on the left, right? So I have to put my matrix that will scale x by 2 closest to my matrix of points so that that happens first. And then the next transformation is the rotation. So I put that on the other side, right, of the scale x by 2, put it on the left. So these 2 matrices, when you multiply them, you're going to get a matrix of points that is the result of scaling all these points, the x coordinates, by 2. Once I've done the scaling, then I do the rotating. So you would multiply these guys, then take the result, multiply by this guy, and then finally I have to do the translation. Right? So this is my translate matrix. Right, there's no such thing as matrix division. This is my data matrix, so let's just label that. So those are just some points that I'm going to be transforming. So I have to come up with 3 matrices that will give me these transformations. All right, so from the notes, let's go back and look. My translation matrix has the identity in the upper left, and then it's got HK, the translation dimensions, in the right-hand column, HK1. So we can fill that one in. So this is 1, 0, 0, 1. HK is 3, 1, and then you put 0, 0, 1 in the bottom. Yep. Yeah, so a translation matrix is always going to look like this. The only thing that changes is where the 3 and this 1 are the translations in X and in Y. Okay, so then let's look at how to do the other kinds. Any other linear transformation, which the rotation and the scaling are both linear transformations, you set up a matrix that looks like this. You've got zeros on sort of the outer part with a 1 in the corner, and then A is the standard matrix for that linear transformation. So I need to create, I know that these are going to look like this. Oops. And then I need to fill in the remaining spot with the standard matrix for that linear transformation. Rotate 90 degrees about the origin. So let's create that. We learned how to do that earlier. I'll remind you. So standard matrix for 90-degree rotation in R2. So a standard matrix is determined entirely by where the unit vectors go. Remember E1 and E2? So here's E1, 1, 0, and here's E2, 0, 1. Okay, so 1, 0, when you rotate it 90 degrees about the origin, where does it go? 0, 1. And then look at E2, 0, 1, rotate it 90 degrees about the origin, where does it go? -1, 0. These resulting points form the columns of your standard matrix. So my standard matrix for this rotation is 0, 1, -1, 0. Familiar at all? We did it out of several classes ago, I think. So that's how I fill in my rotation matrix, 0, 1, -1, 0. Yep. Oops. One more matrix to fill in. I need the standard matrix, this 2 by 2 standard matrix for when you scale X by 2, scale the X coordinates by 2. So let's do this again. Standard matrix for scale X by 2. So again, you just have to know where E1 and E2 goes. E1, which is 1, 0. E2, 0, 1. If you scale this X coordinate by 2, where do you land? 2, 0. And if you scale this X coordinate by 2, where do you land? 0, 1, because 0 times 2 is still 0. So my standard matrix A, the columns are just these points. 2, 0, 0, 1. That's going to scale your X coordinates by 2. Because I'll just show you quickly why. This is 2, 0, 0, 1. If you multiply by xy, you get 2x plus 0y, 0x plus 1y. Okay. So that took my xy and it sent it to 2xy. Scaled the X coordinate by 2. Make sense? Okay. So 2, 0, 0, 1 goes in this last spot. All right, so I asked for just a single 3 by 3 matrix that would perform all 3 rotations. So you just have to multiply these 3 matrices together. Yes, you can use a calculator. And in fact, I think I already did it. Have it written down. Oh, nope, I didn't. I ran out of room. Yeah. Okay, so if you were to do it by hand, start from the right and go left, or left and go right. So matrix multiplication is not commutative. So I can't ever switch the places of 2 of these matrices, right? Like I can't just go whoosh. But it is associative, which means it doesn't matter like if I do these 2 first and then multiply the result by this one, or if you do these 2 first and multiply the result by this one. Right? So as long as you don't ever like swap places, you can associate them. The parentheses don't matter, right? So like if I have 3 matrices A, B, C, right, I can do A, B, and then C, or I can do B, C, and then A, as long as I don't change the order. Okay? So yeah, let's have the calculator do this for us. All right, so I got to put in these 3 matrices. Three by 3 and 1, 0, 3, 0, 1, 1. I know, 0, 0, 1. Quit. Matrix. Edit. B. 3 by 3. 0, negative 1, 0, 1, 0, 0, 0, 0, 1. 2, 0, 0, 0, 1, 0. Yeah. And 0, 0, 1. Okay, so I've got them all in there. I haven't double checked them. Usually I double check everything, but just so we can be fast. So I want to do matrix A times matrix B times matrix C. So this is my matrix that will perform all 3 of those transformations with 1 multiplication. 0, 2, 0. Negative 1, 0, 0, 3, 1, 1. So let's just double check. The reason I had you do it by hand in the first step is to see if this matrix multiplication comes out as you expect. So I'm actually going to multiply this by my data matrix, which is 0, 1, 1, 0, 0, 1, 1, 0, 1. So I need one more matrix D. Three by 3, put in my data. 1, 0, 0, 1, 1, 1. Okay, so I have this matrix here already. I'm going to multiply that matrix by my data matrix D. And these are the points I get. 2, 1, 1, 3, 1, 1, and 3, 3, 1. No, no, but some of your homework questions just ask for the matrix. So I did it like that so you can see how to get it. Yeah, if you want to use it on a different data matrix, yeah. Yes. Okay. Okay, so my points that this data matrix it says that my new points of the triangle that I transformed should be 2, 1, 3, 1, and 3, 3, right? These are my points. The ones don't matter. They were just things I tacked on there so I could do matrix multiplication. Are those the points I got when I did this by hand? 2, 1, 3, 1, and 3, 3. Yeah. This point is 2, 1. This point is 3, 1. And this point is 3, 3. So that matrix multiplication did send my points where I was hoping it would. Half the class, one problem. All right. The matrix of the transformed data. I don't know. So yeah, this says that the 3 points in the data matrix, which were 1, 1. So 1, 1. Sorry, that was not one of my points. 0, 1. 0, 0. And 1, 0. Those were the 3 points I started with. They get transformed to 2, 1, into 3, 1, and into 3, 3. Okay. So when we did it just by visualization, that's what we got. And now we have a way to get a matrix to do that for us. It seems like the visualization is way easier, but when you have to do this for like thousands and thousands of points, it's way easier to program a computer to perform a matrix multiplication on every point. Make sense? Okay. All right, one more with the projection thing. All right, so we have S is a triangle in R3. So it's not a very complicated object, three-dimensional object in R3. It's just a triangle. And we want to find the image of S under the perspective projection. So imagine this triangle models some kind of molecule or something, right? And we want to project it on a computer screen. And we're going to assume that the eye of the viewer, which is called the center of projection, is at 0, 0, 10. So we're 10 units away from the computer screen. Okay, so this is an important transformation for 3D graphics. It allows us to view and manipulate 3D objects on a 2D screen. All right, so the notes said that you just take this matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, negative 1 over D. But in this case, D is 10, right? So I'll just put in a 10 there. Because that's D, the distance away from the viewer. And then 0, 0, 0, 1. That's my matrix that will transform my points. So then I put in my data matrix, 7, 3, negative 5, 1. I'm adding the ones to make homogeneous coordinates. 12, 8, 2, 1, and 1, 2, 1, 1. So I do this. This is the first step. We just do this matrix multiplication. And we're not going to be quite done, but this is the first step. So that matrix, again, came from following the line from the viewer through a point XYZ in the 3D object into the XY plane. And this is the matrix that represents that transformation. All right, so we go matrix, edit, 4 by 4. Negative 0.1, 1. All right, so there's my matrix A, and then I'm going to put in my matrix B will be my data matrix. This is 4 by 3, 7, 12, 1, 3, 8, 2, negative 5, 2, 1, and 1, oops, 1, 1, 1, matrix A times matrix B. Okay, so here's my result. 7, 3, 0, 1.5. 12, 8, 0.8. And 1, 2, 0.9. So these don't quite have the form that we want. We want these things to come out as X star, Y star, right? Something, something, 0, 1, right? So I'm going to scale each of these vectors by 1 over the thing in the fourth entry. So 7, 3, 0, 1.5, divide every entry by 1.5. So now I do my scaling part. So I get things that look like X star, Y star, 0, 1. Yeah, so in this first vector, I'm going to divide every entry by 1.5, because that will give me the 1 in the last entry that I need to make this look like I want it. So I'm going to do 7, just that vector. Each vector has its own scale factor. Right, so my first vector, the first column, scale everything by 1 over 1.5. Second column, you scale everything by 1 over 0.8. So this will be 12 over 0.8, 8 over 0.8, 0 over 0.8, and 0.8 over 0.8. And then the last column, scale everything by 1 over 0.9. So now this is going to give me a vector that looks like 14 thirds, 2, 0, 1. 15, 10, 0, 1, and 10 ninths, 20 ninths, 0, 1. So my 3D coordinates, 7, 3, negative 5, get mapped to the 2D coordinates, 14 thirds, 2. And my 3D coordinates, 12, 8, 2, get mapped to 2D coordinates, 15, 10. So maybe I'll write that out. So, yep. So my 3D coordinates, 7, 3, negative 5, get mapped to 14 thirds, comma 2. And 12, 8, 2 were coordinates in 3 space. And I mapped them to the coordinates in 2 space, 15, comma 10, using the projection, following the line from the viewer through the point in 3 space into 2 space. And then finally, 1, 2, 1 got mapped to 10 ninths, 20 ninths.